Welcome to the presentation on the ideal gas law and molar volume. You'll need your periodic tables out for this. We're going to be looking at the periodic tables, a couple different things on them, including the molar volume, which is on the bottom of the front page. So let's take a look at the ideal gas law. The ideal gas law is our final gas law that combines all four factors into one equation. And here's the equation. PV is equal to nRT. Again, we have the four factors: pressure, volume, the number of moles, and our temperature. So it combines all four factors. So whenever you're given a word problem that contains all four factors, you know you have to use this gas law. And it'll just give you one pressure and one volume and so forth. So we have this other factor that's sitting in there right now, this R value. So what is R? R is called the ideal gas constant, and it is a constant. It's a set number. You don't have to memorize it. Just have to know what it is and what it is all about. This constant is the same for all gases. It doesn't matter what gas it is. It's going to be the same number for all the gases. It contains all the units, so it doesn't just have one unit like temperature is Kelvin. Pressure could be atmospheres. This R value contains all the units, and we'll see why that is. Basically, because all those units are going to cancel out in the end. There are going to be actually three values for this number R, depending on the pressure units that you're using. So you're going to have to choose which R value you're going to be using based on the pressure. And these are the R values. You can see you would use 0.0821 if you're in atmospheres of pressure. You would use 8.314 if you're in kilopascals, or you'd use a 62.4 if you're in millimeters of mercury or torr. So the whole key is to decide what units of pressure you're in and then choose your R value accordingly. Also, make sure that your volume is in liters. Notice that these values are all in liters, so you're going to have to convert. And we know that 1,000 milliliters is equal to 1 liter, so that's the first thing you're going to want to do. So convert liter or milliliters into liters. A lot of times in the lab, we measure things in milliliters, a lot more user-friendly unit. Let's do an example. What volume does 0.0355 moles of hydrogen occupy at 0.651 atmospheres of pressure and a temperature of 29.5 degrees C? First thing you're going to want to do is write down your knowns and unknowns. PV is equal to nRT. So write down your knowns and unknowns. Pressure. It says 0.651 atmospheres. Question is what volume? So that's where your question mark is going to be. You're given the number of moles, N, and you're given the temperature, 29.5 degrees C. Again, you need to convert that into Kelvin. So you need to add 273 to get that unit in Kelvin. And then we need to look at our R value. We choose our R value based on the pressure in atmospheres. So this particular R value, this 0.0821, uses atmospheres as one of the units. And there's the units on that R value. I told you, I mentioned before that it contains all the units. That's the unit. Liter times atmosphere divided by moles degree Kelvin, mole Kelvin. So it contains all those units, and we'll see where that or how that comes in a minute here. So what we need to do is first write down our knowns and unknowns, and then write down the formula we're going to use. PV is equal to nRT. We need to solve for V. We're solving for V. We need to get that on the side by itself, and what we can do actually, we can just solve for it right here in our formula. And so now we know that V V is equal to nRT divided by P. And now we can just plug those numbers in. We'll just put it over here. V is equal to, now we need to find N, 0.0355 moles. Next thing we have is R. That's going to be our 0.0821 liters times atmospheres over mole times Kelvin. We need to have all those units in there. And then we have times our temperature. Temperature, again, we need to convert it to Kelvin, 302.5 Kelvin. And that whole thing is going to be over our pressure, 0.651 atmospheres. So now we're looking at units. You can see this R value of units contains everything, but now they're going to cancel. Here we have our moles right here, and they will cancel with the moles over in that R value, because that's what it is. It's liters times atmosphere divided by mole Kelvin. So basically, you have moles in the numerator, moles in the denominator. Same thing with Kelvin. Here's our Kelvin in the numerator, Kelvin in the denominator. Now if you look at the whole big thing here, the whole big divide here, you have atmospheres in the numerator, you have atmospheres in the denominator. Those will cancel. And you will be left with liters. And that's what we're looking for. We're looking for a volume in the end, so that's going to be liters. So what you will do is multiply these together. Multiply and divide. Your 0.0355 times 0.0821 times 302.5 divided by your 0.651, and you'll get your answer of 1.35 liters for your answer. Not a lot of room on this page. On your sheet, you should have a little bit more room, make it a little bit clearer to do. But again, like always, write down your knowns and unknowns. Very important to do that. Write down the formula, and then you can solve for your unknown in the formula, and then just plug the numbers in, or you can plug the numbers in and solve like we've been doing the other ones. It doesn't really matter, whatever way is easiest for you. All the units will cancel. Remember to choose your R value matching your pressures. Make sure your volumes are in liters. This one we're calculating liters, and your temperatures in Kelvin. So keep those in mind. Keep those things in mind. Real gases versus ideal gases. This is the ideal gas law. It assumes a few things about gases that aren't really true. So let's take a look at what an ideal gas is and what a real gas is. An ideal gas, according to this law, it takes up no space. That's not really true, but for these calculations, it pretty much holds true. Also, there are no intermolecular forces. That's another assumption of an ideal gas, because there is a lot of space in between these atoms, these nuclei, and so there's really not a lot of intermolecular forces going on there. An example of a real gases actually do take up space and have attractive forces. Most of the time, these work, but there is one case where it really doesn't work very well. So real gases behave like ideal gases, except at low temperatures and high pressures. This makes sense if you think about it for a minute. If you have a container, just imagine a container of some sort with some gas in it, and the particles are far apart. They're moving pretty fast, and there's no intermolecular forces going on there. However, if you take that pressure and reduce it, basically confine those particles into a smaller space, the particles are going to get closer together, and so there's more of an option or more of an opportunity for them to be attracted to each other. Also, with low temperatures, the particles slow down. When something slows down as they're going by each other, again, more of an opportunity, more of a time frame there so that they can be attracted to each other. So the particles are closer together because of the high pressure. They're moving slower because of the lower temperatures. And so ideal gases will not behave like real gases at that in those cases. So it's very important to remember that. Low temperatures, high pressures. There will be a test question like that. Molar volume. Switching gears a little bit here. This is where your periodic table comes in. If you look on the bottom of your periodic table, like we did when we talked about the mole, we saw that a mole is equal to 6.02 times 10 to the 23rd particles. It also equals to the molar mass. And the last part that we hadn't covered before is this volume, 22.4 liters. So these calculations will work exactly the same way as you were doing before. So they're all going to be right on the bottom of the periodic table. You're going to do your calculations the exact same way. So if you look in your packet, page 13, problem number 1A, says calculate the number of moles contained in the following gas volumes. And here we have our 5.38 times 10 to the 4th milliliters. Notice that the conversion of 22.4 is in liters. So that's the first thing we're going to have to do is convert it to liters. We know that 1,000 milliliters is equal to 1 liter. So that's what we need to do our conversion. If we start with what we're given, 5.38 times 10 to the 4th milliliters, we need to put milliliters in the denominator. And then we'll put liters on top, and then we can start plugging the numbers in. We have our 1 liter over 1,000 milliliters. So we do that calculation, and we end up with 5.38 times 10 to the 1st liters of hydrogen. We're looking to get to moles. So again, it's going to be your standard mole conversion. Do your conversion factor. Start off with what you're given. Put your liters in the denominator since it's in the numerator here. We're also looking for moles. We'll put moles there. Then you look on your periodic table. Wherever it says moles, you write 1. Wherever it says liters, it's 22.4. So just plug those numbers in just like we did a couple of units ago with the mole. Take your number, 5.38 times 10 to the 1st times 1 divided by 22.4, and we will end up with 2.40 moles of hydrogen for our final answer. Again, it's key. You must convert it to liters in order to do this calculation with the 22.4 liters per mole, because that's what the definition is. In your packets for the ideal gas law, it's on page 11 and 12. Numbers 1 through 6 are due, and 7 through 9 are extra credits. So again, not a lot of problems due, plus some extra credit, just 3 problems to get some extra credit out of it. For the molar volume, all you need to do is problems 1 through 3. That's it, 3 problems, and that's it. So not a lot of problems to do. And again, you'll have time in class to work on these. Ask me questions whenever you need to. That concludes our presentation. Hope you enjoyed it.